Now, before we go any further, we'll need to estimate how thick the atmosphere is. We're going to need to know this because we're going to want to work out, for example, how high we need to go to get above most of the atmosphere to avoid drag. Now, I googled this and the answers came out a bit confusing. One page told me the atmosphere is 300 kilometers thick, another one told me it's 10 kilometers thick, another one said it was 80 kilometers thick. Okay, that's not very useful. And why are the estimates so varied? Well, if you think about it, the reason for that is quite clear. The atmosphere doesn't abruptly end at a particular height. If you plot the density of air against height, it'll be quite dense near the surface and will drop off as you go up and get thinner and thinner and thinner. But it never quite goes to zero. Well, it actually does when the solar wind pulls it away, but even the solar wind has some density, so the density never goes quite to zero, even in deep intergalactic space is 1 atom per cubic meter. So how do you say how thick this is? Well, you can't say where does it end, because it never ends. Perhaps what's more meaningful is where it drops to half its initial value, or something like that. Now you can see this in images. Here's a picture taken from space of the horizon of the Earth, and once again you can see that the atmosphere is thick and gets thinner and thinner as you go up. So that's why the internet has such varied answers to how thick is the atmosphere. It's because it's actually a stupid question to ask. It depends how you define it. You tell me how you define thickness for something that doesn't have an edge, and then I'll give you an answer. So what it probably makes sense is something like where it drops to half its initial value. Something like that probably makes some sort of sense. How can we estimate that? Well, first of all, let's use our general knowledge, also known as common sense. Now, I know you're not supposed to use that in physics classes, but hey, this is Ninja Physics, we can get away with it. Do we have any general knowledge about how thick the atmosphere is? Well, we know that when you go to a high mountain, you can get altitude sickness. I spent a lot of my time at the summit of Mauna Kea observing at 4,200 meters, and you definitely notice there's a lot less atmosphere up there. People living in the plateau of Tibet or Bolivia have bigger lungs and need to acclimatize. So those sort of places are sort of about 5,000 meters up. We know that summit of Mount Everest, it's just about possible to survive without oxygen, but most people carry oxygen tanks. So all that is telling us that the thickness is sort of maybe the 5 to 10 kilometers. So at 5 to 10 kilometers up, the atmosphere has dropped considerably in density, whatever that means. So that's giving us a rough Ninja Physics order of magnitude. Another way to work it out would be using air pressure. Air pressure is caused by molecules of air moving around randomly because of the heat, bouncing off surfaces. So here's your skin, air molecules are ping-ponging off it all the time, and that applies force. We'll come to that later in this course. But the air pressure is absolutely enormous. It's about 10 to the 5 newtons per square meter, which is called pascals as the unit. So 10 to the 5, that's whopping force per square meter. And if you think about it, that pressure has got to be what keeps the atmosphere up. So let's take 1 square meter of the surface of the Earth and a bit of air on top of it. That air is exerting pressure in all directions, that's what pressure does. Particularly it's exerting pressure upwards on all the air above it. So let's have an imaginary column of air going all the way up to the top of the atmosphere, above the square meter. Now all that air has got to have density, and because it's got mass, it'll have gravity pulling it downwards. And that's got to be balanced by the pressure from the bottom, because that air is not moving up or down, it's just sitting there. For something to sit there, by Newton's laws, forces must balance. So the downward force of gravity must be balanced by the upward force, which in this case is coming from the pressure of that slab of air underneath it. So what's the weight of this column of air? Let's say it goes up to the top of the atmosphere. Have we defined that? We're going to call that some height h. So the volume is going to be the area, which is 1, times h. So the mass of that column of air is going to be the volume times the density. The density of air is 1.2 kilograms per per cubic meter, we'll call it 1, so that's about h. Now we're assuming for the moment that the density remains the same all the way up, which of course is not the case. But this is telling us if the density did remain the same all the way up, how thick would the atmosphere have to be? So the weight then is mg equals the pressure. So mg is h times 10 equals the pressure, which is 10 to the 5. So h is about 10 to the 4 meters, which is about 10 kilometers. So if the atmosphere was like the ocean, which is to say uniform density then abruptly stops at some point, the pressure that we have at the surface level, which you can measure using your smartphone or something like that, or look up on the weekly weather report, is about what you need to support 10 kilometers of air, which roughly agrees with our general knowledge. So this all seems to be fitting together. We also know that planes have a cruising altitude of about 10 kilometers. You can sometimes see those screens in the back of the chair in front of you which have a list of altitude, and they're typically cruising at 30,000 feet, which is about 10 kilometers, and you can see that you're above most of the atmosphere there. The air is very thin outside the plane, and most of the cloud tops are about your level. So that's also kind of agreeing with this sort of figure. In fact, you could do the calculation. We'll do that in Physics 1201. And what you actually find out is that the pressure or the density of air at some altitude h is equal to the density at the surface e to the minus height over a scale height h. So it's exponentially declining, which is why we got this shape here. That's a nice exponential decline. And this scale height here, h, is roughly 7 kilometers. So what that means is when you're 7 kilometers up, h will be 7. 7 over 7 is 1, so it's e to the minus 1. So basically every 7 kilometers you go up, the density drops by a factor of e, which is 2 and a bit. So that roughly agrees with everything we've talked about, and that gives us enough information to go with flying cars. So it looks like the density of the atmosphere is dropping off by a factor of 2 in a few kilometers, 5, 7 kilometers, something like that. Then if you go up another 7 kilometers, it drops by another factor of e, and so on. So it all makes sense. That's telling us what we need to know.